Today we will be discussing about live commenting system, and by live commenting system I mean when a video goes live, or let's say a celebrity comes and starts posting about their content live, let's say on Instagram or in YouTube as well, when there is a premiere of a video or there are live events happening on YouTube. You may see the comment section which keeps loading instantaneously with people all around the world who are interacting on the comment system. So how does that typically look like? This is the comment section where we keep seeing different comments appearing. There is a chat, there is a send. So you type your text here and you click send. Your comment will be entering in one of these places, and again you will be keep seeing different other comments. So there is brief, and there is your comment, and then there are incoming new. That's what a live commenting system will be. It's different from the actual commenting situation where there is already an uploaded content and then you go and comment. Those are just people coming it at any point of time and commenting at their own time or day. Here it's happening all the comments at one point of time within the duration of the entire video. Say the video is of 30 minutes, like the event is going till 30 minutes, all the comments are happening. So there will be a lot of implications, even though this is a very interesting point for me because the architecture is pretty simple from the beginning to how we are posting the comments to reading the comments. But because everything is happening on a load basis, like there are a lot of concurrent requests happening, there will be slight tweaks, intelligent tweaks that we'll be discussing about. So let's get started. First discussing that what our business requirements will be, which we also say as functional requirements. One would be post comments, see all comments, in near real time. Now obviously I could have said real time, but then there is nothing called real time. You go near to a real time. I'll discuss about it further. And see all comments posted before we joined. Now this also we all have witnessed. So let's say an event has started and I joined somewhere in between. So till now 10 minutes have passed and there will be a lot of comments that have populated so far. When we join, we see like 20 comments also loaded already in the view window or whatever. Like if let's say my view window can accommodate 20 so comments, I see those past 20 comments so far, and then new comments start populating. That is what I meant by previous. Your comment is like optional. If I have commented, then obviously it will eventually come up over here, and incoming new keeps scrolling. Now I will quickly erase this clutter. And we have also seen what we will remove away from this here is that replying to a comments live is actually not possible. And I mean it is possible, but we have never seen it happening in real-time system. So we will not be discussing this at least. Reacting to comments. So in a live scenario, even reacting to comments is also not possible. It's not that it is not possible. We haven't seen that happening over both YouTube live comments and Instagram live comments. So these are not scope of the discussion. So let's start quickly thinking out from basic principles that what should be happening. Obviously there's the client. Now I will be unifying. Obviously there will be a load balancer and there will be an API gateway. These things are pretty common. There will be multiple different services, and we are only discussing about our commenting service. So for the sake of simplification of diagram, I will unify these two into something called API gateway, which I have already discussed in the video where we discuss about the entire Twitter system design, where I have explained that By default, a lot of cloud distribution providers provide these in a unified format. You can check in the top right section the link to the video. I'll again simplify this diagram a lot. Now this looks much cleaner. Here we are interacting with the load balancer plus API gateway and then forwarding the request to the commenting service. Obviously, prerequisite are that there are other services also which are out of the scope of our discussion. For this live commenting, we have a commenting service at this point, and then we will have a database where our comments get stored. So this will be a DB. What this DB is, I'll come to it quickly, but as simple as we have at least a write path at this point. There are a lot of things hidden in this abstraction. We will start exploring these one by one. Actually, if there were no such load put into it, like what are those loads? There are millions of users who are commenting live on 100 live videos at a given time. If it were only one video and there are a few commenters, this entire thing is as simple as it can get and we are done. But then we are talking about real scale systems. So what are the first principles that we have to think about over here? To begin with, we have two APIs. One is post and one is get. Post is on comment with a video ID. I'm putting it as vid ID, and obviously I'll be sending my comment in this as a body. And in get, I will have comment. We'll have a video ID. But there are so many comments. As I said earlier, I'll draw it out here. There are so many comments previously seen. There are comments which are incoming. We have to also, there is a movement of scrolling up and down. The more, obviously we can't scroll down because they are coming automatically and the UI will automatically scroll. But when the more we go up, we have to fetch. But also at the same time, let's say I am over here because I have scrolled and then again I have to come down. That means we are again scrolling down. Why I said so many things is because this query parameter itself has to evolve, and because we are fetching a lot of, say one video at a 30-minute length can gather around 10k plus comments. It is very easily possible. How do we do it? We go via the concept of pagination, and we are doing cursor based pagination. I mean, there are both the process offset based and cursor based. I go with cursor based because that is more ideal in any given scenario. It keeps things consistent. We'll be talking about why there is difference between both the things in some later video as a technical deep dive. So if I have to evolve it, I write it in this way: comments with ID, and then I start listing down my query parameters. I will write it this way. It's all sequential, but I'm writing in step by step. One would be the cursor, and technically the cursor would be last comment ID, next would be direction. Are we going forward or backward? Forward is this sense, backward is this sense. This is also done. And obviously page size, how much are we retrieving? So let's say I keep 30. So in one shot we are querying 30. All of these are different query parameters and we can keep changing them. Last cursor ID. So just giving a brief, what we mean by cursor based pagination is, this is our table and we have different columns. One of the columns will be timestamp, and one of the columns is comment ID. Obviously this will be the primary key if it is a SQL table. Now when we have to do cursor based pagination, we have to keep it consistent so that every time we fetch using the ID as the anchor point, it's always consistent. How do we do it? We will be putting a incremental sort on the timestamp column. Everything gets sorted in this fashion and we get comments like this: C1, T1. That means we are guaranteeing that if we get this cursor using a sorted fashion, the next 20 will be consistent every time. How this is consistent, That means there is something called inconsistency, and this inconsistency comes when we go with offset pagination, because let's say due to any reason a new comment comes and gets inserted in between or gets deleted, then the inconsistency gets lost. Cursor based makes sure that that consistency is not lost. Now we have spoken a lot about these two API calls. We have made sure that even in this journey or in any journey altogether, our post and get, so basically getting of the comments or posting of the comments is done. We will mark that off, posting and seeing all the comments. But this part is not done in real time. Now comes the interesting part. This is interesting because there should be some basic intuitive ideas coming into mind. When we say near real time, we have to understand, and this will become a common pattern in all the system designs across. Say there are two entities, this is the client and this is the server. Sorry for the handwriting, but this is a big C, so it's client and this is server, big S. Generally all these interactions are happening over the HTTP protocol. Now HTTP protocol is consisting of an entire three-way handshake, and it takes time. Each request that we get to the API via the API to the server, which is getting served to us, happening over the HTTP protocol, each is a three-way handshake, and we are not able to get a real-time sense. What is real-time? If we have to put some numbers to it, as per human brain, if we are getting any response back in 200 milliseconds, that we assume as 200 milliseconds as real time, and this will never happen over HTTP via the three-way handshake happening and the entire round trip happening every time. So this we can understand will not happen via normal HTTP protocol. What options are we left with? So let's go to a new page, and there are two important things. One is a WebSocket and the other is server-sided events, SSE. I'll full form. So generally people talk as SSE, but you should know it as server-sided events. Now they are not that hard. I'll just write their own features over here. Obviously there will be a cut in the video because it will take some time to write them down, but we'll then discuss exactly what it is. Not much. Giving a brief overview, WebSocket is an upgrade over HTTP. What happens is that you take into header request that you want to do a WebSocket. Client sends this request to the server. These two parties then go towards an upgrade. If both are compatible to do this upgrade, then the HTTP will get upgraded into a WebSocket connection. WebSocket is bidirectional in nature. That means now over a persistent connection, both the parties can keep sending and receiving messages. I send, it receives, it sends, I receive, and I don't have to do this handshake each time now. Over one time resource, I can now keep chatting. And other is server-sided event. This is when server has to keep sending and I am not that chatty. So chatty is a lingo that we use. I just need to keep listening to server. Actually the evolution has come from polling. So let's say I were not to introduce these two things. What I would have done is this get request, right? I would have kept polling over it. Every 20 seconds or so I would have polled. Now in a very simple system, this is the ideal way to go. Not only here, like I in my current company, I have done these things where we have polled because we see the traffic. And why to write an extra headache of going to an SSE? Because when you're coding these out, you have to put a lot of infrastructure decisions. Even SSE does not happen so easily, but I'll come and discuss about it a bit. Polling is the way to go. You just keep polling from client every 20-second interval or 30-second interval to the server that is it done, like what is. So I keep doing a get request and I keep getting my answers. But at least here, given that there is a lot of concurrency in place, a lot of users are out there who would be requesting for the recent comments, we cannot keep doing polling. So we have to choose either between a WebSocket or an SSE. So now is the time. I'll just snap for some time and write down what it is. And here we go. We have all the content here we need. WebSocket, as I said, it's bidirectional. Both client and server can equally communicate over this channel. It has its own protocol. It is like an upgrade over an HTTP. And all parties need to upgrade. So you must have heard, or in case if you search, people will say WebSocket is resource incentive. So what is the intensity in that resource? This is that entire thing. Is a full negotiation over all the parties that need to upgrade. What are all the parties over here? If we come back, there's the load balancer, there are the proxies, there are the firewalls. Everyone has to negotiate this upgrade. If there is any small problem in one of the places, the WebSocket will not be implemented. Now that does not mean that it is very hard to implement. Actually, these are just server configs you have to change, and that's it, the entire thing, because we are able to control everything from this point. Client just has to initiate the WebSocket request. So it's not like it's very hard. The only question remains is that, do we really need a bidirectional channel at this point? Our writes are not as frequent as our reads. And that is why WebSocket is a very good candidate for any chatting platform, because both the members are very chatty. Rather, we will go with something with server-sided events. It's very easy. It's unidirectional. Server is the one which is giving all the data points. It is over HTTP only. It's no upgrade needed. Browser is having built-in support over it. Like, it takes care of as simple as dropping of connections. In case there is any problem in the connection, the browser will make another attempt to reconnect, and then wherever it had stopped earlier, it will get data chunk. And this is the chunking. In case you guys don't know what how the SSE response looks like, there will be like a data chunk and it will keep getting data. To give a brief glimpse of how it might look, in case today you might be looking into the responses from LLM, they are coming. It something comes like I am happy and ... like rest of the parts are also populating. So all of it is happening actually over an SSE, where LLM is generating the chunks and each of the new chunk is getting as part. So first data was I, next data was I am, next data came I am happy. So accordingly all the entire rendering is happening. Now here in terms of LLM response, I made the data chunk in this way. Here you can understand in terms of comments, C1, C2, similarly this way the entire data chunks will be coming up. Now again putting this arrow over here. Now that we have established the main pillars, WebSocket and SSE, we can clearly understand that our main candidate here would be an SSE. So what we will do over here is, I'll copy this entire diagram and place it below. So as I have copied, I'll write it again, comment service, and as I said, now once initial request has been, then it will be an SSE at this point, and we'll start communicating with the communication comment service, and we will be appending it to our database. What is the database? Again, I will not be discussing quickly right now. Obviously, it is something which is highly available over eventual consistency, so you know the answer at this point, but we'll be discussing a bit after some time. We'll be discussing further over here that how we can improve it further. We have done a lot of heavy lifting. We are almost near real time, but how do we scale it up? For example, if a peak load comes and our autoscaler kicks in, scaling means as simple as drawing a new box over here. But SSE is like a parametered connection. A connection will be having some of its own credentials. If not credentials, they are headers, because when you are sending data chunks, then it also needs to know that last chunk what it has sent, and with respect to it, other set of chunks it will send. So there are a lot of meta information that needs to be stored when you go over something like an SSE. That means it is no more stateless, it is stateful. And that is where the complexity starts coming. So as I had said earlier, even though it's a very simple design, but because of the high amount of load that we are handling, it starts becoming a bit tricky. but it's a very graceful solution. So the main problem that we had right now is each one has a state of the SSC or the multiple different clients that are connected via the SSC for getting the comments to them. We can do one smart thing at the very instance right now. We have a write service altogether, and these are the read services. Why? Because if I have to make a write via the load balancer, I will do a normal post request and it will hit the DB. A person in their lifetime, whenever they are on a live commenting video, they will go at max with 4 or 5 comments. Even if they go with 10 or 20, it's okay. We can handle that load over this path. It's the read, it's the vast amount of read that we have to scale up. So first of all, we have separated concerns. So I'll quickly change the arrow. Obviously, a get request is done and it will be converted into SSC, but it's a read entirely. The next thing is we have to manage different states. How would the states look like? Again, giving you a brief idea of what I mean by different states over here. It's something like, for video 1, these are connection objects. I say con1, con2, con5. For video 2, I say con3, con6. I'm just randomly numbering something, and so on. These are the different states that every one of them have to manage. And what we mean by this is, for video 1, connection 1 has the entire metadata for the SSC connection, and say the client has to read about video. Obviously video 1 means the video ID 1, video ID 2, because we recognize by the video ID parameter over here, video ID. So using the video ID parameter, we check, and then all the different connections. So basically it's a server-sided event. The server, once the connection has been established, the server will now broadcast it to all the connections which are established over video 1. But the moment scaling happens, say this pod dies or a pod newly comes up and new clients get assigned to the new serving pods, then how will all the servers combinedly take this decision to whom to send? Because for any instance, let's say due to scaling issue, video 1 gets, one of them has video 1 with connection 1, the other video 1 has connection 2 and connection 5. This is on pod 1 and this is on pod 2. That is where the entire problem starts happening. That state, even if there is a state, there is no common consensus. There's a distribution of state. That means the state should not be part of the system anymore. It has to be extracted out. And that is an important first principle thinking that we have to do. So just deleting this part quickly. There has to be a common state manager. Now, that is something a bit of a high end saying that there should be a state manager. Should it be a DB? Should it be a cache? If we think a bit more smartly, we don't even need a DB or a cache for this. Or we need, it should not be a DB or a cache, it can be something else as well. But why not? We create something called a pub sub system. That means the moment we do a write, the only thing that we need to note is, let's say the write happened for video ID 1 via the client C1, or let's say connection 1, then it will be notified over the pub sub, and all those servers which are interested, because pub sub happens by the concept of topic. I'm abstracting a lot of things out here, but you have to understand that in a publisher subscriber model, there are subscribers and there is a publisher. There will be multiple topics. Irrespective, let's say there is only one topic. There are incidents happening which are getting into the publisher system, and whichever they have subscribed, it gets pushed to them. So here they want to know which videos are getting comments, and that is getting pushed to PubSub, and then they will start reading from the PubSub. That's it. And we have solved the state management concept altogether. Now, let's say this has C1 and the other has C2, C3. They all will have subscribed to the same topic of video, and actually this thing will not happen. The main thing is this will also not happen. Why? I'll come to a minute. They will subscribe to the same topic and they will consume it, and they will get this and they will send it back to the respective clients, like C1, C2 and C3 will see all of these, all of the comments that had been posted. But the point is, when we are distributing and we have the concept of auto scaling, we will make sure that different viewer groups basically are co-located. That means, let's say for video V1, C1, C2 and C3 are watching it, and for V2, C4 and C5 are watching it. Then we co-locate C1, C2, C3 into the same instance, and C4, C5 into the other in these pods, and that is how the scaling will happen. So basically there will be a load balancer who will be distributing that load and making sure that these get directed and co-located into particular things. This is one way to solve it. There is also other way, which I was saying as state manager. What we wanted to save is which instance, like which of the servers is managing which, is handling the request for which video to which connection. And then we go with the concept of zookeeper. Obviously I will be copying the this entire diagram here, so there will be a cut in the video, and here we go. So again, to iterate what we have achieved, let's for some time forget that there is a PubSub existing, so that I will again revise what I am trying to discuss over here and what the actual problem is that we were facing. There are two different paths here. One is the post path and one is the get path. So basically one is the writing path and one is the retrieval or the reading path. The moment we have done a post, we are storing it in the database. But how do we at the same time send it back to this? Let's say there were 2 or 3 users who have kept their YouTube video open and they want to see the live comments, and let's say C4 is the one who made this comment. It has to be broadcasted into these. That is what happened. With the moment we made the path separate, the write is going into the DB, and we have to somehow make sure that all these writes have to be now broadcasted back. So if let's say we were scaling it out because of peak load, we don't know that for video 1 who are the intended connections that have to be broadcasted that information. And that is where we were talking about state management. And even without state management, we can also do it via PubSub. So basically there is a state management. It's just that the publisher subscriber abstraction is maintaining that. Again, I have drawn it out, but if I go back over here, that's what I was trying to say. The entire state has been managed by the PubSub itself via the concept of topics, and from that all of this has actually subscribed to the needed topics and they are getting all that information. So that's what we have done. Or otherwise we could have gone with a concept of, if you think about it, this will be a term that you will listen. It's called zookeeper. Technically speaking, it also does the same thing. What it's doing is, in zookeeper will have a configuration wizard called Z nodes, and what they will manage is all the information within the Z nodes, like what are the different servers connected to that, not connected, but what are the different servers which are responsible for video ID, and then that server will be equivalent to what connection metadata is present in that. So it's something like, I'll quickly just give a brief on my understanding. There will be something called server object. There will be something called videos object. In videos, we'll be doing a mapping of video to different server S1, as to here there will be server object 1 and its meta info, there will be server object 2 and its meta info. So you get the point. So that's what Zookeeper is, the management in distributed system design. It is the one which is doing a high frequency management of state. Obviously databases could have done it, but the database is very low latency, very high latency for this kind of scenario. I mean, even though we can choose Cassandra or something, but the kind of consistency that we need, because pods can fail and there are other things, that is where Zookeeper is used. When I do a technical deep dive into the exact infrastructure of Kafka or let's say DynamoDB, you'll get to see that Zookeeper is the actual interior department which handles it. So we could have done the same thing, right? Once it does, then there will be a communication happening that it has to reach out and push this information here. So it will reach out to the Zookeeper. It will check, hey Zookeeper, I need to see this information, that where is this particular video and who is handling it. The moment it gets that information from Zookeeper, it will then reach out to. One level of optimization we can do is, we can cache this also over here, because it's one instance. We can cache it over here and it will not reach out to Zookeeper every time. We will put a TTL over here because at times new connections can keep coming. So yeah, that's it. After some time cache will expire, it will again do a read to the Zookeeper and then it will push it out. And a kind of overall, I had said that we can go with the PubSub model as well. Let's say I put a Kafka or Redis queue over here and our life becomes very sorted. We have to also mention the term called topics. What are topics? For example, this again, there will be a dedicated PubSub video, but because I have given a brief about it, to help you guys understand, PubSub topic means, let's say there is, in terms of class analogy, because topic is related to subject. Let's say there is a subject matter related to science and there is subject matter related to English. Obviously very naive example, and I say there are user 1, user 2, user 3, user 4. User 1 is interested in science, user 2 is interested in English, user 3 is also interested in English, user 1 is also interested in English, and user 4 is interested only in science. So these are the concepts of topics. So basically this is the entire publisher which contains individual topics, and subscribers subscribe to topics. Publishers then emit out events to the individual subscribers. Now let's say there is any notice coming that okay, we have midterm exams on science means physics, chemistry, blah blah, and user 1 and user 4 get notified. If there is a midterm exam coming on English or there is a course assignment due, U1, U2, U3 all get notified. That's as simple as a concept of topic. Now coming on to this model, when we have introduced PubSub, what will be the topic? Topic will not be video ID. Now people could have said, even I thought earlier it could be a video ID, but there will be thousands of videos, if not thousands is a very less number. We cannot just scale up on topics because the entire Kafka and Redis queue will become a bottleneck in terms of the number of topics allowed in these clusters. Rather, we have to be very smart. What we will be doing is, we will be doing a hashing. We will be doing hash video ID modulo n. N becomes the number of services that have scaled up, or that is the ultimate number of services that are present right now, and based on that the topics will be generated, or the other way around. I mean, we can also keep this as the number of topics over here. Yeah, I will reiterate my words back. Obviously number of services is indeterministic. We already know the number of channels, so I will just write it as number of topics / channels. This will be predetermined by us, and based on this entire formula, now what happens is that all of these services don't have to read unnecessarily. So let's say I, or not I, any user just did on video 1 and say many services unnecessarily who are responsible for managing load of video 2, 3 or other composites, but not of video 1, they are unnecessarily listening to it. Rather, if we go via this, only a subset of those videos, if I do video 2, then only a few, let's say S1, S2 and S3, only they get, instead of the 1,000 services that we had scaled up. So we have done a much better, smarter model over here. So that's the only thing in PubSub. We are managing the system, but it has been obligated to the entire publish subscriber architecture, and we are offloading it over there. The only optimization that we have to do is smartly creating the number of channels, and to make sure if there was only one channel, everyone was unnecessarily reading it, and this is like very CPU IO intensive task happening each and every time. Like everyone is doing randomly writes to every video, and unnecessarily everyone is getting a wake up call, which is not actually needed. So we are doing just that, only a subset. Only I wake up at max 3 or 4 services, and that's it, we are done. Why did we go to this complexity actually? Just to put some good numbers. Generally, I don't talk about non-functional requirements that quickly, but here there will be some, just to give a scale. We are scaling to 10 power 6, that is millions of videos, and with around 10 power 3 comments per second. Then the other will be, we are giving availability. I'll come to this. This is the final part, but I have already answered it a bit earlier. Then consistency for comments. It's because obviously the moment I have commented, I don't want to see that comment. I'm not even least bothered. I'm more concerned about low latency comment broadcast. That is reading comment in real time. And by real time, we mean almost close to 200 millisecond. That's it. This is how we achieved it. By keeping an SSC connection and scaling the read request services to as many as needed, we can easily reach low latency count of less than 200 milliseconds. Coming to the database for availability greater than consistency, as part of our CAP theorem, we are choosing a database which provides higher availability and eventually becomes consistent. There are two candidates here, Cassandra and DynamoDB. Both are equal candidates. If for company like YouTube and Instagram, they want to really cut low cost, because DynamoDB charges by requests per second, they will prefer Cassandra because there are a lot of fine tweaks they can do, so that ultimately they store data in format of LSM trees and it goes inside. So how it is stored, how fast an optimal query can happen. Because eventually at the surface, Cassandra and DynamoDB both have the PK and SK, primary key and sort key. And if I were to give a full data schema of the comment, it will be something like comment schema. There will be a comment ID. There will be the video ID, user ID, who is commenting, the content, and created at. As per my previous discussions also, automatically our comment ID is the primary key and this is the sort key. As simple as that. Why? Because when we are doing the query, we have to do it on an increasing order of the timestamp at which they have been sorted, and this becomes the sort key candidate via which we can easily do a quick. And this is the primary key, obviously. As simple as it can get. So that kind of solves all our functional and non-functional requirements. These are actually our non-functional requirements because we have matched it with numbers, even this. And coming over here, this number is not actually a determining factor. It is more like helping us understand how many resources we need. Why? Because when I said I have to scale up each and every instance, and each instance is involved in doing an SSE, as per what I understand, if I have a very optimal hardware condition, I can handle around 10 power 6 SSE connections optimally. And I said that there are 10 power 6 into 10 power 3 connections. Basically that is a multiplicative number, and by 10 power 6 that means I need 1000 services. That's it. Means if I scale this to around 1000, or for a buffer I keep 120 more, like that's we do generally, like not 120 more also, we can keep 20 more also, like keep a buffer of 20%. That's it, we are done. 20% is 200. Sorry for my calculation at this point. So yeah, that's it, we are done. 1200 servers scaled up at a very peak capacity is not a problem, and we don't see this kind of peak every other day. But still, if we see, still it is not a problem. It can be scaled down easily based on the RPS parameter. So yeah, it is a very easy system on a surface, and even in a deep dive it is still easier. It's not like we have done something extra. It is just that the moment we start scaling up and there is a state management that has to happen, that state has to be extracted out of the entire system and it has to be managed by someone else. Now how it is done smartly, either by Zookeeper or pub subsystem, because ultimately there is a lot of system that has been separated out. The write request which is happening over this path has to be conveyed back to the reading service, and that too we cannot wait over DB by putting a CDC over here which will understand, and that becomes a overcomplicated route that we are going through. Short circuit will happen via this write service itself, which has to communicate. But for communicating, either it can choose the Zookeeper path, keep a cache for some efficiency and then do it, or otherwise just go to a pub subsystem, notify the pub subsystem that hey, this for this video this content has been published. Now these have been, obviously the moment a service spawns up, it will be subscribed to one of the particular topics based on this particular formula, and then they will be notified accordingly, and they will then use their internal mapping which I had kept over here. It will go and reach out and it will just notify all the connections over via the SSE, and that's it, we are done. Now we will discuss something interesting on these lines. Maybe we'll go deep dive into one of the individual services later on some of the future videos. Till then, keep watching, be subscribed, and hope you enjoyed the entire thing. If in case there are any doubts, please reach out in comments and I'll be happy to reply. See you folks.